All right. Hi, everybody. Welcome to this session. It's called the Framework for Knowledge Organization and Modeling of Space Data from Astronomy to Near-Earth Space Activities. Can you see the screen share all right, or has it not come in?
Here it comes.
Yeah, we got it now.
Oh, can you see it in full screen mode, or is it in?
Yep, it looks great.
Oh, okay, fantastic. So again, welcome everybody. I'm Rob, and I'll be organizing this session. To begin with, in the Zoom, if you're not familiar, you can send messages in the chat on the bottom right hand of your screen in the Zoom window. I'm assuming everyone is in the Kiko chat, if I have that spelled right anyway. And you can go to the session description page, as well as the session agenda page, and let me just send the links in the chat, put the links in the chat if people don't have them. So this is the agenda, but I think it's already there. And let's see. Yep. Okay, that looks good. I'm back to screen sharing. Sorry, folks, trying to juggle a couple of things here. All right. Finally got the hang of that. Okay. So once again, welcome to this session. Today we'll be talking about space data, a little bit of graph technology, knowledge management, organization, and representation. The anticipated speakers include Kurt Cagle from Data Science Central. I'll be your organizer. I'm a member of ESIP clusters and partner organizations. Most relevant for this particular topic is I'm an affiliate at a Center for Orbital Debris Education and Research. I'm also an aspiring PhD student, actively applying and open to programs. And I'd like to take the time to acknowledge Indigenous history and cultures in our respective regions. Now, for some preliminaries, for some context, by space data, we mean very broadly data about exoatmospheric space, or commonly known as outer space, the phenomena therein, observations of that space, space science data, data collected from satellites, data about satellites and their activities and contents. And this varies from astronomy to astronautics. Examples include astronomical data, as well as subdisciplines, spatiotemporal data, remote sensing and Earth observation data, spaceflight data, astronaut data, as well as various forms of data from human space activities. I'll put my camera off for connectivity issues. So the roadmap for this session, after this welcome, part one is going to be the first speaker, pending some technical issues, followed by breakout sessions or a group discussion. And part two is going to be second speaker, myself, followed by further discussion, and we'll close after that. So some questions for the audience. On the session agenda page, there's these questions that are listed here. for a full list of questions and to also just answer them if you're willing. You can also go to that link. And to connect the dots, how we relate the first speaker to the second, speaker one is going to speak on some interesting concepts in data science and graph technology, some contemporary topics, which can serve as food for thought, as well as some potential applications for innovation, use case discovery, and support for both your data needs and the project described in speaker two. Speaker two is going to be speaking on knowledge representation for space, providing a specific example project, as well as a call for interest and support for it. Now, in terms of a big picture, if we take a step back and sort of examine the activities for relevant for Earth science investigation, we have a general focus on Earth science data, and rightly so, for proximity and practicality and human impact, self-understanding, and to help humanity right here on Earth, naturally. So it's development on Earth, knowledge discovery and innovation as purposes. But by also looking outward, we can better protect Earth and humanity's positive development. And in doing so, we safeguard both life and property on Earth and in space. And we also ensure that space science research affords us the opportunity to comprehend local and cosmic phenomena and their interrelationships to us on Earth. It also allows us to identify the impacts on life activities and inform safe spaceflight. Excuse me. Finally, it also allows us to develop humanity and cultures beyond Earth and foster discovery and innovation in that process. So I'm going to briefly stop here and see if there's any update on our speaker. My apologies again for the technical issues. I think I'll just continue. We'll change the order and we'll do the second talk first. All right. So moving to the second talk, which is going to be on space knowledge modeling. Just to give some context, so my focus areas are conceptual data modeling, formal ontology, and these other topics with a specialty focus on space or astronomical and other types of space-related topics, specifically for knowledge representation, semantic modeling, and that sort of activity. I also have focus areas unrelated to that and broader things such as ethics, the ethics of AI and data, as well as methodology. Although unrelated to space, if there's any maritime folks here, I also have a partial background in maritime operations and training and search and rescue, which is the only other passion on equal intensity as I have for space. You can find some relevant articles at the link there. I serve extensively in various communities, giving volunteership and service to discipline. This includes serving in committees in standards organizations, both national and international, education committees, space data, nonprofit organizations, semantics, maritime safety, and aerospace as well. As I mentioned earlier, I'm an aspiring PhD student, actively applying and searching for opportunities, and you can contact me at the details below. Now, an overview of this particular talk. I'll be going over some background concepts for knowledge management and organization. Then we'll get into the specific domain topics and data. We'll also go over my sample project, its tasks, methodology, the modeling itself, and I'll provide a short demo of an application of some of that work. and then finally end with a call to action and a call for support. So in a nutshell, what is this particular project? So the project is aiming at developing a suite of knowledge organization systems for space. Why should one care? Well, potentially to help with your space data needs, as well as to address interdisciplinary questions and explore interdisciplinary questions. Given the type of techniques and technology involved, it could also apply to pedagogy, so educational endeavors, and in general, just to foster innovation and creativity. Now, what problems might it solve? So given the topic of knowledge management and semantic technology and knowledge organization, it includes potential benefits such as content search and retrieval, the development of metadata and vocabularies, synonym support, interoperability at semantic levels, more broadly and more abstractly, crossing disciplinary boundaries. It also includes clarifying concepts and conceptual data modeling for activities and techniques such as model-based systems and engineering. And of course, to be determined. So part of the idea is to brainstorm and innovate and identify collaborations to see what directions and benefits this project can do. And a minimum goal-directed question is, what do domain experts and data owners understand their data to mean? And is it open to interpretation? And with those questions and the goal of creating knowledge organization systems for that data, how can they be useful? And these questions, of course, can be asked across the spectrum for any project that does knowledge representation or semantic modeling, that sort of thing. So this is the project, my project description site. You can access it at those links. And I won't do a demo of that, but for your information. Now, getting into some background topics, knowledge management. It's been defined in one way as the acquisition, creation, usage, and representation of knowledge. Now, that involves quite a bit, and indeed, knowledge management is a wide field, and it involves a number of activities, and that ranges from knowledge gathering to knowledge organization and structuring, refinement, and distribution. And we'll be focusing on the organization and structuring aspect. So knowledge management involves the formal expression of knowledge for problem solving, not always, but at times. And this is related to a branch of artificial intelligence, which is called knowledge representation and reasoning. And this activity of AI is essentially asking the question, how do we capture human knowledge in a way that automated systems or information systems can act autonomously in the world and perform tasks in the world. So how does knowledge management relate to a particular type of knowledge organization system, which are ontologies? So the knowledge organization and structure activity of knowledge management has been described as being done through ontologies. And ontologies are one tool or technique or system in the knowledge management toolbox. And so this diagram represents various types of so-called knowledge organization systems, and the overlap and dotted lines indicate that it is a bit fuzzy. The boundaries, the descriptions of these are a bit fuzzy. And so some of these systems have actually been used as other systems in this diagram. So conceptually, distinctions can be made, but in practice, it's not so simple or apparent. Now, focusing on ontology engineering or ontologies, it's been defined in this way as the set of activities concerning the development process and the life cycle and the methods for building computational ontologies. And a computational ontology itself effectively defines the terms and relationships comprising a vocabulary of a given topic area, as well as the rules for combining those terms and relations. Now, I'd like to expand a little bit on computational ontology because it's not quite so straightforward as one might think if you're coming from a purely terminological or linguistic perspective. So there are quite a number of definitions of ontology, and one of my personal projects is cataloging various definitions and cognates of the term ontology, and that link goes to that project. They're sometimes called semantic models, conceptual models, knowledge graphs, and so forth. And there's various ways to develop them, various methods. There's automated ways, there's manual ways, and so forth. And interestingly, you can develop computational ontologies to various degrees of complexity, size, and abstraction. Sometimes they're, as I mentioned, used as other systems. They can actually be used as a database as well if you have the right tool. And effectively, as we saw from the previous quotes, it's a knowledge organization system that effectively has grouping terms or categories and linking terms. And and collectively, they're basically just metadata. And they're capable of being formally defined for computation and formal semantics, and structured like a taxonomy. And they're capable of having constraints specified on them in order to restrict the meaning of that vocabulary. So you reduce ambiguity and confusion, and that allows you to form computable expressions for tasks like automated inference and data queries. And computational ontologies have been described as acting as a semantic layer, providing an interpretation of the meaning of data elements. And of course, they can be linked together, although that is both an activity and a challenge unto itself. Lastly, we see that having various models, such as ontological models or semantic models themselves, are resources that can be looked up, means that all data is self-defining. So basically, the ontology or conceptual model or semantic model allows data to be self-describing, and they allow data to be understood independent of the format or technology and the vocabulary used in disparate communities. But I'll add two things to that point. Methodologically and ethically, it's important to ask: is a given model expressing the intended, desired, or correct meaning of a data owner's data and the words that are used to annotate that data? Additionally, a second point: having various knowledge models, even for a similar topic or different topics, it allows us to compare, create, and identify models that may be desired for a given data set or a topic. And it allows us to determine how data owners would like their data to be semantically described. And naturally, a data creator or owner or a subject matter expert is most probably the best person in a position to know the meaning of their data. So the project today includes tasks to explore various distinct models for the given topic, domain, or concept. So what is the topic? So the scope is effectively natural astronomical phenomena on the left here, orbital debris, micrometeoroids, human space activity, and spacecraft, as well as abstract concepts related to space. So basically spatiotemporal relationships, and how do we include causal relationships as well in that? Now, what's the data? So the relevant data here, scoping this project also, is things varying from observational astronomy to remote sensing of the outer space environment, and that can be both space and ground-based. Spaceflight activity, which goes into space situational awareness, telemetry data of artificial satellites, data catalogs of observed Earth orbiting objects, and may include in situ experiments for which scientists interested in collections or samples would be relevant. Some example data are these statistics for Earth orbiting satellites. So on the left side here, we see effective total numbers of active spacecraft by country. On the right, we see a trend of increasing number of space trash, as it were, so debris. And this has been growing due to a number of particular events and increased human activity. So, for instance, focusing on the upper right-hand corner of the graph, we see two events, or I should say, a particularly impactful event of the collision of two spacecraft in orbit, which drastically increased the number of debris in our Earth orbit. So right now, some statistics are there's approximately millions of debris less than 1 centimeter in diameter, and there's about 1 million 1 to 10 centimeters, and about 20,000 greater than 10 centimeters in diameter. So this topic of orbital space debris has been, for me, a particular interest, and we are seeing increasing numbers of these debris objects, and as well as the data, as we have surveillance and observational capabilities increasing as technology gets better. And naturally, there's an impact both on astronomical and astronautical data, as well as knowledge acquisition. So the astronomy community, for instance, is seeing is facing a problem of both debris and active spacecraft interfering with their astronomical observations. So there is both impact in orbit as well as on Earth. And this brings us to my particular project. And I encourage anyone with questions to also feel free to speak. But for this particular project, it's in progress. I conceived it in around 2011. It's a bit ambitious, and it's a personal project. It's effectively creating a set of linkable modular ontologies, a suite, as it were. The methodology to date has been manual ontology development rather than automated. And it has both theoretical, abstract, and technical questions and goals. Some of the tasks in the project can be both distinct, standalone, but also related to the overall modeling effort. Again, the one of the links here goes to the description site, and for this, I actively seek support, as it is a personal project. Now, some approximate statistics so far: about 11 written works, about 21 presentations in 5 countries. I've written about four relevant reports, manuals, or co-authored on committee manuals relevant to space data. I've co-authored and contributed to a U.S. national standard in the aerospace community for space data architecture concepts, and to date won award through ESIP's Funding Friday, which I'm grateful for. Now, to expand on the domains of interest or the selected topic areas, if we start at the top, we see the relevant topics that the project aims to address. So on the left-hand side, we have astronomical phenomena, once again, and that includes things like celestial bodies, observations thereof, astrometeorology, also called space weather, data collection, analysis, and computational modeling. In the middle, on the far right, I should say, we have astronautics or spaceflight, and that includes things like particular spacecraft, their subsystems, data collection from them and about them, and ground support systems which support the spaceflight mission. We also have interdisciplinary geopolitical aspects, because it is quite a complex interdisciplinary field. the actors thereof, as well as some management and policy aspects. Now, very critically, it also includes situational awareness activities, which involves observation and surveillance, and of which orbital debris is a critical element. And that naturally involves data collection, analysis, modeling, and prediction, of course. In the middle, we have overlapping disciplines for topics ranging from natural astronomical study to artificial human activity for spaceflight. And naturally, that includes everything from physics to orbital dynamics, and in between that, spatiotemporal concepts. And the idea here is to understand both natural phenomena and our artificial phenomena, and the data we collect about both. And the context, of course, is outer space. And the idea here is, what's the impact on both Earth and cultures, and what is the causal structure of these of this impact? So some terminological projects which might be of interest to some folks here are both standalone and related to the overall modeling effort. And these tasks in terminology involve effectively creating living catalogs of both vocabularies in their entirety and an examination of particular terms and their definitions. And so at these links, I have descriptions of some of these in progress catalogs, and effectively this serves as research for this project as well. Some of this on the right side, some of this work has been used in some committee work in the aerospace field, in which particular terms have been examined as well. So in terms of the modeling, this diagram represents a general overview of some of the tasks and the knowledge representation modeling efforts. So again, the project is aiming at a living suite of modular ontologies, as well as other forms of knowledge organization systems. I've tentatively called it the Orbital Space Environment Domain Ontology Project. And the living catalogs I just mentioned, which are natural language terms and various definitions, they provide sample vocabulary and target content for the data semantics, the metadata, and related applications. The domain data in particular provides key indicators of relevant content, informing both the development of these models and the knowledge representation activity itself. The conceptual engineering and domain research aspect of this project allows us to explore various architectures, scoping approaches, and modeling possibilities for patterns and knowledge organization systems. And now, as I mentioned, it is in progress. It's actively open to formal support to sustainable development. And on the bottom in the green, we have some particular deliverable products that are goals. In the center, we have particular modules or ontologies for a given topic area. And the project also has involves some independent project plans, but related given the space topic as an overlap. So some example ontologies or knowledge graphs that are in progress. One is the orbital debris ontology, which I spoke on in 2015, and that involves providing a computable vocabulary knowledge model for categories of debris, the characteristics thereof, some causal provenance or history, environmental aspects for that environment. Another ontology is the space situational awareness ontology, and that essentially involves capturing the activities and infrastructure that allows us to attain awareness of the orbital environment, and that includes observational data as well as tracking data. Two other ontologies for which I'm interested in getting support are the astronomical environment ontology and a knowledge graph for near-Earth space. Now, this is related to the my Funding Friday presentation, which is at the link below. Another ontology is a space weather or astrometeorology ontology, and this is displayed in part in these images. So in the center, we have effectively a conceptual model diagram, which I've taken in a causal context to effectively link the phenomenon to the effect that it causes. On the right, we have screenshots of some of the terms for this particular topic. Now, the independent projects that I mentioned, the project plans include these, and these can be standalone projects, or they can be linked with the domain ontologies in the overarching project. So some project plans include design patterns, as well as ontologizing, so to speak, other knowledge organization systems, such as vocabularies, exploring distinct conceptual models for a given topic, and further developing external ontologies involving expanding vocabularies, natural language definitions, and formal semantics. Now, for example, this slide shows some screenshots of astronomical terms in a ontology editor. And the idea here is to identify some similarities between the terms, so effectively a terminological, semantic, and ontological comparison, and identify paths to potentially merge or other activities for these ontologies or vocabularies. Now, a notional vision is of a space knowledge sharing network. So if we consider what would a knowledge representation or knowledge modeling component look like for trying to share information or data in a network form for space activities and space science, and how can it link to various other techniques and technologies such as AI, model-based systems engineering, machine learning, and so forth. And now, it may be potentially scalable or applicable to both individual enterprises or consortia of enterprises, as well as globally, so across the particular space through which the data is transmitted. And what are the pros and cons of this particular type of technique or approach? And on that note, consider this internet concept from NASA. So we see here basically a concept of an internet technology for the solar system. And so a question is, how can knowledge organization systems, how can the ontologies of this project be of utility to applications or technology concepts such as these? And similar to that, in 2016, I presented on my overall project, and this diagram basically encapsulates part of the vision. So we have space actors or agencies or persons or organizations at the bottom that deal with space data. Above that, in the greenish color, we have the data itself, and that might range from databases of orbiting objects to astronomical databases of astronomical data, and so forth. In the blue, we have the ontology models I'm developing, and altogether, the idea here is to form a linked structure which may basically have no boundaries. So it might be at an international level. So if we imagine an international information system, what is the potential utility of having some sort of structure like this? And in the yellow, we have potential benefits for the space community. In terms of methodology, to date, my approach has been manual ontology development, and it effectively includes some of these tasks. So at the very top, we have documentation, and That includes the creation of specification documents. Below that, we have subject matter research and study, for which there may be various particular subdisciplines. And that also includes the collection of particular content and general awareness of how the natural language terms are used in various communities. Now that includes disciplinary knowledge, the data sets themselves, and jargon and local vocabularies. In red below that, we have conceptual modeling, graph diagram creation, symbolic logic, and things of that nature. Below that, we have the modeling itself, the ontology development or knowledge organization system development, which includes terminology development, defining aspects, creating any metadata associated with that, assigning identifiers, tool exploration, and implementation aspects. Below that, we also have mappings and crosswalks to other vocabularies, as well as the exploration of use cases and applications. Now, some output goals include some of the products I mentioned, which include catalogs of terms, their examination, comparison of definitions, catalogs of existing resources, as well as knowledge catalogs and effectively a library of the conceptual models or ontologies that the project aims to complete. And in terms of exploratory aspects, what is the potential for plug and play of some of the concepts that are defined in these systems? And the idea of a dynamic ontology is also interesting, in which we might have a system that can change in order to update based on changes in the particular topic area. Now, if we expand on the particular task of vocabulary development and formalization, on the left here we see that both conceptual analysis, natural language consideration and natural language considerations, as well as subject matter research and meta modeling, may inform and be sources for the development of the local ontological vocabulary or other types of knowledge organization systems and their vocabulary. Now that leads into the creation of definitions, which vary from natural language to computable, and the degree of expressivity will vary accordingly. Below that, we have non-local vocabularies, which can be mapped to the ones being created. And on the right-hand side of the screen, we have an expression of the knowledge representation tasks. So after the collection of domain knowledge in natural language, that is translated into symbolic logics, such as first-order logic, non-classical logics, that sort of thing, and as well as computable languages. And the idea here is to output effectively a catalog of that translation. Now, in terms of a diagram, the diagrammatic or visualization aspect of the effort, these are some diagrams, conceptual diagrams I've created for particular topics, and this varies from spacecraft and their components to broad overview of the orbital debris context to orbit categories and other aspects. Now, going towards formalization, we see here an example of the orbit categories I mentioned in one in progress ontology displayed in an ontology editor, and having a partial taxonomic structure, distinctions are made, and the categories can be logically defined according to particular data parameters and desired value ranges. Now, moving towards the formalization aspect, in first-order logic, for instance, and computable languages on the left-hand side, here's an example of first-order logic formalization of a a generic statement or piece of knowledge that that one might want to represent. On the right-hand side, using the computable language common logic, we also see the syntax for implementing a formalization of that statement. Additionally, now since the idea of the project is to explore various formalization languages, this is in a fact-based language called object role model, and each element of the diagram structure has a logical meaning. So it effectively allows you to encapsulate the intended meaning through the diagram itself, with the under the hood logic that is in place. Now, this is a visualization of one of the ontologies that are in progress, and naturally, it'd be interesting to explore various sorts of visualizations in order to communicate the ideas better. In terms of the documentation tasks, so some in-progress documentation products include ontology requirement specification documents, of which the literature talks a good deal. And this involves the specification of some focus areas for the project and desiderata and its purpose and so forth. Other documentation products include in-model documentation, so that's effectively the annotations in the ontologies themselves. And I also have in progress a local metadata ontology for the models that I'm creating. Now, in general, the project may serve as a library of knowledge organization systems or models, knowledge representation and reasoning models for the space topics of interest, as well as in contemporary terms, maybe a digital twin. So we hear the phrase digital twin being talked about often. So this may be a semantic digital twin of sorts for the things like the space environments and spacecraft systems. So this brings us to a demo portion. I'd like to show you some work that a colleague of mine. I see we have our speaker, which is great. So we'll get to that shortly. So I'd like to now have a demo of an application of some of my ontologies with a colleague out of one of the NASA centers, in which we rendered a 3D interactive solar system using R, JSON, one of my ontologies, and a editor tool. So give me one moment and I'll switch to that. Okay, tell me if everyone can see the. Lost that for 1 second. I have to go back to it. Okay, can everybody see this screen?
Yes.
Okay, fantastic. So this is the 3D rendering of the solar system, and this represents an interesting application area for the knowledge models, and effectively using the editor tool as well as one of the ontologies, the output was displaying this table of some of the orbital parameters of the solar system planets. Another visualization in that particular application was this. Another diagrammatic interactive solar system, and likewise the work used the concepts encoded in the ontology for some of the orbital parameters of the planet's orbits, and output the particular values for each one of those in a table. Now moving back to the last slides. All right. So in summary, a goal for the project is a unified but modular knowledge graph and ontology suite for the selected topics from astronomy to spaceflight, as well as being open to bespoke space and spatiotemporal models, knowledge organization systems. So if the idea is if one needs a vocabulary or a metadata set or an ontology for those topics, that's the interest. So these are some goals, and you can contact me once again at these links. Now, finally, as this is a personal project, and it has been for quite a while, I am continuing to actively seek ways to do this in a formal and supported manner with experienced professionals in the respective fields and mentors and that sort of thing. So I'm quite open to be a PhD student if someone is interested in the project, or assistance with business development or employer support or some sort of formal work collaboration or sponsors. And I'm certainly open to ideas on how to do this in a sustainable and supported manner. So please reach out to me if you know anyone that would be able to, or if you're interested. Now for Q&A and discussion on this, some questions I have for you are, what do you find interesting? How can it help with your work or others' work? What are some use cases and applications? And that sort of topic. So on my side, I thank you for your attention.
Hey, Robert, I was wondering, we had a question in the chat if we could share the GitHub repo link for those demos, either in the chat or if it's already on the document.
Okay, for that, I'd like to, because I think we're low on time. If the person can reach out to me, we can
Sure.
talk about that later, because we have to get to our speaker as well, if that's all right.
Okay, perfect. Yeah, I think that should be fine. Is that okay, Miranda? I'm sure it will be fine. Great.
So if no one has any questions, or we can go to our speaker. Okay, so I think we'll go to our speaker, Kurt Kegel. And let me just bring up the original introductory slide. Okay, let me screen share one last time here. Okay, so I should correct that. All right, given that we had the order changed. All right, so our speaker is Kurt Kegel, and he's the managing editor of Data Science Central, and he's an invited expert with W3C and IEEE, focusing on knowledge graph, on graph technologies, excuse me. And I will leave it to Kurt to screen share.
Right, sounds good. Apologies to everyone for the bit of initial chaotic work. We had some signals get crossed. So I'm going to go ahead and share my screen. As I'm doing so, just a second. Okay, so there's that. And let's try this. Okay. So there's this one. And,
Yeah, that looks great.
everyone. Okay, excellent. So mine is fortunately very, very short. And I I appreciate the chance to be able to talk with everyone here. Again, I'll give you kind of a quick introduction. I am the managing editor for Data Science Central, or datasciencecentral.com, and have been focused primarily on taking the site, part of the TechTarget network of sites, into the future, essentially exploring a lot of areas, including graph technologies, ontologies, machine learning, IoT, other areas like that. So as a consequence, a lot of the work that I've been focused on lately hasn't necessarily been directly attributable to astronomy. Now, I do have pretty much by happenstance, I actually have a degree in astronomy. I've never had a chance to use it. I've always been a programmer, but I do have a degree in astronomy, and it's something that's been it's been a focus of mine for a while now. But what I wanted to really talk about today was actually to talk about the metaverse and how the metaverse actually impacts a lot of the directions that I think that technology is going to be going, and especially with areas like astronomy and the like, where we're dealing with large amounts of data with lots of different information coming from different organizations. Because of that, a lot of the focus that I'm looking at now is really kind of looking beyond what Robert was doing with the ontologies themselves and looking a little bit more at the architecture. So some of this that I'm going to be covering today is actually a little more focused on areas that I think people should concentrate on, or should be on the lookout for moving forward, so that you know, as the technology becomes more mature and as the ideas essentially become more solid, then what will happen, I suspect, is that it will have significant impact for anyone that happens to be in the astronomical aerospace, you know, really aeronautic space in general, as well as anyone outside of that domain that happens to have interest there or elsewhere. So my talk today is specifically on metaversal architecture, or what does the metaverse have to do with space rocks? So there's a lot of different questions that you run into when dealing with ontologies and designing ontologies. And there is a perception, ultimately, that when you are working with ontologies, almost invariably people think about the issue of things and relatedness to things. But what they don't think about is essentially the aspects of time. And when you're looking at an ontology, and I've written a number of ontologies over the years. I've worked with Fortune 500 companies. I've worked with government agencies. I've worked pretty much across the spectrum with regard to the kinds of industries that we're dealing with. Time always ends up changing the dynamic of how we think about information and how we think about content moving forward, or how we think about the relationships that get involved. And to a significant extent, when we're looking now at the metaverse really does revolve around this whole notion of what exactly is time and what exactly is space, and how do you define and why do you define everything in terms of those particular coordinates. And that's because time represents change, and everything changes. There is nothing in your ontology that will not change over time. And if you don't understand that ontological principle and can't articulate it within the ontology or the data set that you're developing as part of that, then what you have is basically insufficient for any kind of real world application. You have to be able to deal with time and the measurement of time and how that impacts our perceptions of things. What's worse is that when you are talking about change and how that change occurs, you also have to take into account the fact that there is always a lag in the system. And one of the big challenges that I've run into, among other things, I'm working currently with the Spatial Web Foundation to help articulate an IEEE standard regarding kind of the broader integrative aspects of all of the components that you need for describing a metaverse, an augmented reality system, or a digital twin type system. And most of those really do come down to where am I, when am I, and what kind of frame of reference am I currently dealing with. So if you look at it from that perspective, then the one thing that you ultimately come back to is that the vast majority, not necessarily all, but most ontologies are basically ways of solving logistics problems. And that's an idea that I want to kind of push into this whole process, because if you think about everything in terms of logistics, you discover that all of a sudden, this very flat view of reality becomes much more complex and much more four-dimensional over time. So I'm going to go back a little bit. I loved studying Einstein when I was in college. There is a lot of, everyone who is involved in this field needs to understand the concept of relativity. But for the most part, when we think about relativity, it's high energy physics. It's situations where you're dealing with high gravity potentials and communications, or high gravity potentials and black holes and neutron stars and the shape of dark matter and dark energy in the universe and the whole 9 yards. But what you need to understand about Einstein was that he was actually thinking about frames of reference. Everything that he wrote, certainly everything he wrote in the special theory of relativity and a fair amount of what he wrote in the general theory of relativity, was ultimately about the question of what frame of reference am I in? And it's a problem that we face even today. So this is an important point, and it's something that you have to understand. And always when you're working with ontologies, nothing exists in isolation. Everything exists relative to something somewhere. And this is important because when you start talking about ontologies and talking about graph databases in particular, graph databases are special primarily because they are ideal for describing relationships, which means that everything that you have, all of the terms that you have, and all of the relationships that develop generally are describing entities as they relate to other entities, and to a certain extent are describing entities as they relate to the coordinate system or the frame of reference that some other entity has. And one of the central problems that you run into when talking about any kind of geospatial system, any kind of communication system, is that ultimately you have to be highly conscious about those frames of reference. That means that there is no universal coordinate system. You can't just create a general clock. You might think you can, and in most day-to-day situations, you can generally get away with it. But the moment that you get outside of the gravity well, and you start basically dealing with situations where the invariance involved and the gravitational pieces involved are sufficient, then what will happen is your clocks will begin to drift, and your coordinate frames will end up changing because you have accelerating frames of reference. One of the key things that Einstein said was any accelerating frame of reference is indistinguishable from gravity. We know what gravity is. Gravity is this thing that pulls us to the earth, but it really doesn't. It is that thing which says that I have a relationship to a massive object, and that massive object is something that bends the space-time around us. And we talk about those in basic terms without necessarily understanding the significance of them. This does now become more and more important when we start talking about any kind of IoT device. If I have a satellite, that IoT device is basically going to be in a somewhat different frame of reference. And it must have both a clock and an accelerometer on it to figure out exactly what that is. You can't have one without the other. You have to know basically how my frames of reference matters. Orientation even matters. Where you are pointing matters, because we will increasingly be running into situations where time variances are sufficient that something at the bottom of the gravity well, or something at the bottom of even something like an L5 construct, just so we have the James Webb telescope, has to take into account how it's oriented in space and time, and that in turn is basically fundamental, because we have to communicate with that. We have to talk to these devices, and some of these devices are going fast enough that the speed of light becomes actually a fairly significant imperative. So I spend a lot of time looking at sensors and sensor fields and predictors, which are kind of an ersatz sensor. Sensors are important because sensors basically allow us to determine at a certain space and time locus a bundle of information. Is it raining? Is it warm? Is it windy? What direction is that wind coming from? What's the air pressure? What's the changes in air pressure over time? What's the state of a particular entity? And that kind of information, that set of sensors in general, are going to become more and more important as we essentially develop out the need to be able to create digital twins, which are simulations not of individual things, but of systems. I mean, we already have something in place right now that allows us to a certain extent to identify things like traffic patterns and traffic blockages and things like that through the use of sensors. They're still pretty primitive, but they do exist, and we're moving to a mode increasingly where we're saying, okay, I have this cell phone, this is my little sensor box up here that I'm holding up. Let's see if I can, my little sensor box that I'm holding up, and that sensor box is developing all kinds of information. As our cars become more sophisticated, that sensor information is going to become more and more complex, and is going to include things like, what is my GPS system, which is also dependent upon space-time coordinates? What is my orientation? Anytime we deal with augmented reality systems, you're talking about orientation and position and time as well. Once you start talking about these sensors the sensors essentially become your eyes and ears into the world. And as the noosphere, as the information sphere becomes more sophisticated, that coverage of sensors is actually going to become more and more overt over time. However, typically we don't actually talk to a single sensor. When we're working with information, we are more often than not talking about information that's actually collated through some kind of an intermediate store. And it's that intermediate store that we end up actually querying. And that's a secondary, but again, a fairly critical idea. When you're dealing with information, with data, you're very seldom actually talking to the sensor directly. Sometimes you can. More often than not, no. What you're looking at is essentially what is the report of that sensor over time. And that's because of a number of factors. One is computational bandwidth. Another is security. Now, you don't want someone basically spoofing what's happening with that sensor. And to that extent, you want to be able to operationalize and secure the information that those sensors have, which means that any kind of system that you have that is talking, that is maintaining data access, is likely to end up being one step further in terms of building out the building out this picture of what things look like that's accessible to a larger overall view of what is reality on the ground. So as a consequence, when you're thinking about this, you begin to move away from this idea of just simply being able to say, okay, I want to know what sensor 2256 in this field is actually telling me, to I want to basically get what sensor 2256 told this device that I can query. But in order to do that, I have to recognize that there is now latency in the system. And so a significant amount of the work that's being done now in terms of describing metaversal concepts, the full immersive reality, augmented realities, supported realities, and so forth, really kind of comes down to how much of an approximation can you get away with and still have something that's useful. The other aspect that you come into when you start talking about these is that you're essentially generating fields. Fields are very important. Fields are basically ways of saying, I have a map, either in 2-dimensional or in 3 dimensions, that essentially assigns to a particular space-time point, locus, a particular value, and that value may be temperature related, meaning it's something that's a scalar, it doesn't have a direction. It may be vector related, it may be tensor related. The idea of essentially saying I have a tensor that sits on a point is actually a fairly intriguing one, because it means that you can talk about n-dimensional spinning objects, rotation in space, as essentially being distinct from the grid that you're working with. And one of the things that you're now seeing in a lot of geospatial work is essentially this movement towards thinking about, okay, rather than I have a rectangle that identifies things, I basically created a tessellated grid. And that tessellated grid can then give me all kinds of field values that I can use as maps overlaying the construct that we're working with. The key thing about this, though, is that every sensor that you have has a global identifier. And this is actually a very important point, because one thing that we run into is with the virtual world is that there is no physical thing that is actually holding the world together. The closest that we have, or at least the attempt at the closest we have, is something like a I don't think the term is right, a piece of work, but proof of work, thank you. With blockchain, where you basically say, I have a computation that gives me value. Other than that, everything exists only because it has an identifier. And that's a really profound concept that we're still trying to get our head around. But it's critical when you're talking about development of ontologies, because if you have things that are given as identifiers, then you basically have to both determine whether those identifiers are clearly articulated and are distinct, but also to determine when they're not, how confident we are that the thing that we're looking at is in fact the thing that we think we're looking at. So I talk about the concept of a predictor, and a predictor is essentially a mathematical model that interpolates loci upon imaging solutions. Says, okay, here is something that we're seeing with a camera, and we're trying to interpret that as a car. And that car is moving from point A to point B. As it moves from point A to point B, what assurance do we have if it passes around the building and we see it coming around the other side? It's the same car. If we can't see it or we don't know it, what is the likelihood that that path is going to continue along the same path that it currently was on? And so there's a lot of calculations that basically get involved, a lot of modeling of intent that also gets involved when you're basically trying to map the real world to the virtual world. That means that everything has an uncertainty that grows over time, unless you have some way of going back and saying, okay, I have a sensor value that I think is the same thing because it happens to be a green Mercedes-Benz. Not that there are many of those. And typically, these are things that
5 minutes,
have significance. Okay, thank you. So when we look at it, a sensor with a low sample rate can be seen as a predictor. I'm not going to get into this other than to say that because of this, we're trying to build a model, and those models that we're building are essentially going to either be scenes or they're going to be projections on the worlds that we're creating. While I'm at it, and we may have a few minutes on questions, but I will try to make this slide deck available. So I want to kind of walk through this. Once we talk about these, we're basically talking about information that forms into scene graphs. And those scene graphs could be potentially huge. We have things that represent entities. The pictures that Robert was showing earlier are a pretty good indication of what of a very small set, but you start talking about tracking all of the millions of space rocks and debris and other things like that out in the sky. And one thing that you begin to realize is that that information, the interactions, those information become very, very problematic. And when you start talking about all the things that you want to track, then the other question of this is basically, 1, can I represent it? 2, can I find it? 3, can I make it part of some query that we're wanting to work with? So a lot of the creation of virtual worlds and AR worlds really comes down to trying to figure out what level of detail that you're currently working with in terms of the kind of content that you have. And that applies as much to space as it does to here on land. Search becomes very important. In fact, I would say search is probably the most important aspect of the metaverse. We have to be able to find things. Because we have to be able to find things, we need to be able to say, how do we pull information? How do we collect information and categorize it to be able to contextualize it? If I have a means to contextualize it, then I have a means to search it. An ontology provides a language for contextualization, but no ontology itself is universal. Any ontology we build is going to be problematic. Additionally, because a lot of the metaverses that we're talking about are also essentially simulations. What if something changes? How does that affect things? We need to be very careful about thinking about how do we effectively search things that don't actually exist except as simulations, as differences. Now, this is Laniakea. It's the largest structure that exists in the universe. And, finding anything is probably somewhere in there, but it's kind of useless if you don't have a good search mechanism. So one of the things that I would recommend very strongly is people pay attention to a project going on with the WPC called SOLID. SOLID is, in many respects, I think, one of the most important concepts, or one of the most important things being produced by the W3 in the last 20 years. It basically is a way of creating a distributed web of federated, capable, interactive, secure databases that anyone and everyone can utilize to be able to get to present information, to store information, to seek information. Once you have this kind of solid interface made up of solid pods, where each pod is essentially its own standalone database, and probably virtual in that, then what you're doing is you're essentially creating networks of knowledge graphs that allow you to be able to find things. And I think that in many respects, we're kind of at the next stage of abstraction to where we were in 1991, when we started talking about networks of web pages. Now we're basically talking about networks of databases. And that's going to change the dynamic of how we search. It's going to change the dynamic of how we change time. It basically is something that is going to profoundly influence the kind of environment that we're working with over the course of the next 20 years. I think that once this happens, I think it's going to be a replacement for blockchain. I think it's also going to make it much easier to granularly secure information so that only those people that have permissions can do so. Because it's a consistent architecture, you can basically apply search patterns and retrieval patterns in a much more consistent way. And that solves a lot of problems. You can also take documents, including images, and decompose them in much the same way. Similarly, you can start dealing with sensors and actuator nets, essentially as pods that are abstractions of these entities, so we can communicate with these sensor nets as if they were databases. This is a really powerful concept. Federation becomes trivial because you can basically pull in multiple information from multiple pods simultaneously. It utilizes concepts that are just now beginning to come online, including decentralized identifiers and verifiable credentials to make sure that the reference ID that I have is in fact referring to the thing that I think it is. So in many respects, I think that what is starting this year, probably within the next few months, you're going to start seeing pods being deployed everywhere. And it's something that you should look into in a lot of detail, because I think it's going to become truly, truly significant. The last is basically just kind of a summary of what it is. The metaverse is not the 3D web, but the 3D web is part of the metaverse. The ontologies are basically important to maintain consistency, but we have to be aware of the fact that ontologies change. We have the infrastructure to be able to communicate deep information because it's basically decomposed and broken into parts. It is a contextual network, a powerful contextual network, and context is everything, but only selectively. So thank you. I appreciate the time, and again, I'm apologizing for the foobar earlier in the presentation. But if you have any questions, please let me know. Also, if you're interested in writing for us, we're always looking for writers. Thank you very much.
Thank you very much, Kurt. That was great. You raised a lot of important and valuable points, so thanks so much. So we have a couple of minutes left. I'd like to open the floor to anyone who might have comments or questions on either of the presentations, Kurt's or myself, and and your ideas or ideas for collaboration, how things might help your own data or others. Yeah, so I open the floor to anyone.
Everyone's getting tired. This is getting close to dinner time, I can tell.
Well, some things I found interesting with Kurt's presentation. I thought the particular topic about time and change was especially important. It is a very, it's both a challenging and a critical aspect of modeling, is to how to capture variation and change, and things are not static, and that's one issue in things like knowledge organization systems and modeling in general. So I thought that was pretty valuable to raise the point. I also found the project solid. That sounds interesting, and I think maybe audience members might want to explore that as well. Does anyone have any questions or input or ideas?
I have one. I'm curious if you've heard of SPACE, which is a metadata ontology for space physics data that's out right now. That was SPASE.
Yeah, actually, someone else mentioned that. I was aware of that, but I never actually understood quite what the content was going for. So it's something I need to look into more. Are you involved in that project?
Yeah, I've been involved in that for the last decade or so. Just helping to describe data sets and model output. But it's a way of, yeah, just providing a unique description that then can interoperate with automated, bots and web pages and stuff to help discover and find data sets and their metadata descriptions. And it includes a lot of things, but it's an interesting project. And your talk kind of reminded me that would be an interesting thing to get you and a couple of the space experts together to chat.
Yeah, that'd be fantastic. Please, we can talk offline if you're open to it.
Sure.
Does anyone else have any thoughts or what they found interesting of what Kurt was talking about, or myself, or just the topic in general? All right, well, I'll invite everyone remaining to feel free to go to the agenda page and put your thoughts there. There's some questions as well, and this is the end of our time, so I'd like to thank everyone for joining, and happy 22. Thanks to ESIP and our support here. So thanks to Kurt, and hope everyone has a nice day, and feel free to reach out. Thank you.
Thank you, guys.